Okay, recording has started. And I hope you can see my screen. Minimize this. All right. Sorry for some delay. Some issue with my laptop, I think. All right. Let's get started. We're going to talk about problem solving a little bit, and then move towards planning in this lecture. Last time we have seen this. Let me just quickly go through this as a recap. Problem solving, like we have certain assumptions, like agent knows world dynamics, world state is finite and small enough to enumerate, world is deterministic, and utility for a sequence of states is sum over path, and agent knows current states. So when we pose the problem, like as we have certain assumptions, and these are the basic assumptions we have, and with these assumptions we move forward. So we also talked about an example of route planning in a map in the last lecture, where a map is the entire world, right? So say if you have cities in India, instead of worrying too much details about real world scenario, what we do in the problem setting setup is abstractize the problem or make an abstraction of it, and this abstraction is what we represent as a graph, right? So a map is a graph where each nodes are cities and links are roads. We do not really worry about how bad the roads are or how good the road is, but at some level of abstraction, we just worry about they are connected, and right. So agent know the world dynamics. What does it mean? It means that map gives world dynamics starting at city X on the map and taking some road gets you to city Y. So you actually know, like if you catch this road, you are going to reach this city. Then we have like the set of cities is finite and enumerable. Taking a given road from a given city leads only one possible destination. The utility for the sequence of states. Utility for sequence of states is usually either total distance traveled on the path or total time for the path. Then the final assumption is like agent knows current state, so that is similar to like you know the where you are current city is known. Then we also talked about a formal definition of what problem is, and we said like a problem is nothing but a five tuple where we have this set of states denoted as capital S, and you have S naught, which is the initial state, and you have operation, which is nothing but a function from set of states to set of states, and operation is like, okay, you move right or move left, right? So such operations are there which actually if you are in some particular state you move to some other state. The other one is goal test, right? So goal test is you know what is the goal, and at current state whether that state is the goal state or not, right? So that's what is the test. It's a Boolean function which is from set of the states to binary values, true and false. Another thing is the post, right? So post is again a function from a sequence of set operations, the sequence of sets and operation to a real number. So how the problem is defined here. Now let's briefly talk about like search. I'm sure this is already covered in the EI1 itself, but just to have the context. So search is in very abstract term. These are the three steps you do in search problem, right? So if you formulate the problem as a search problem, this is what you do. You first put the start state in the agenda, right? And then you loop for these two statements. First is the get a state from the agenda. Right? If that is goal, you are done. Right? If the state itself is the goal, that then you are done. And if it is not, then expand the state and put children in the agenda. Right? So if you are children in the agenda, then you will go to this and keep on doing this. So in very abstract term, these are the three steps you do in any search problem formulation. Okay. So again, this is something which you have already seen. Is uh, there are two type of broadly two types of search techniques. One is ununiform search, like the breadth first search, depth first search, or like uninformed cost search. Right? So we'll see this. What is it? And there is informed search where uh, like A star search. So let's quickly look into this by writing. Just a minute. Hope you can see on the screen. Right? So the two types of secret search techniques. Very quickly, I want to just discuss a few of them. So let's see if we can use it. So search techniques. Let's call it a recap. Techniques, right? So we said that there are two types of search. Right? One is informed search. What do you mean by informed search? At every state, you are really sure about what is where is the goal, right? How far from the goal. So this is kind of, you know, her goal or agent, let's call it, agent is from the goal. Right? So every state you really know this. The other one is called ununiformed. Uniformed. So this is not uniform, ununiformed, uninformed search, where you really do not know, right? So the agent does not know how far it is, how far it is from the goal, right? So, like, for example, if you are like techniques like BFS or DFS, the popular techniques, they are really don't know where the things like. So, let's say this is a city A, city B, city C, D, E, and let's say E is the goal, right? So let me mark like this. So this is goal. Right? And you just do not really know, and every coast is same here. So there is no concept of coast here, right? So this is kind of a coasts. You can assume that to be one, right? And what you do in BFS, you use choose. So I'm not going to describe the algorithms of BFS and all, but you use queue and you use DFS, you use stack and try to find out the where the just a minute, right. So when what you try to find out is you are at starting state. A starting state is known, goal state is also known, and your objective is to find the goal state, right? So let's say this is your start state, and this is your goal state, and you can very well do it using BFS or EFS. What if you have these courses are not uniform, rather they are non-uniform, right? So if they are like the cost is different for different, what I meant to say is following. So just give me a minute. So the cost is also ununiform, uniform, and the costs are also non-uniform, right? So they are different costs associated with different cost. Different cost associated with different cities between different cities, right? So if that's happening, how do you do this? So let's look into one example. What I'm trying to say, a good example. Right. So what I'm trying to say is you have a start state which is known. You have a goal state which is also known. So this is goal. and the costs are not uniform. Like, so there are different costs associated with different nodes. 2, 3, and split. This is a goal. This is 1. This is 2. Cost 3. Cost is 6. Cost is 1 here. And then there are some other nodes, let's say 5, 4, 7. Some cost associated, and these costs are not uniform. Then how do you approach this problem? Again, you will be doing the same UC cost technique, non-uniform cost technique. And what you do is you start with S, and then you use priority queue here, right? So you have a priority queue. What is the priority queue does is, let's say you start at S, then you have two options to go here. So if you can either go in this way or this way. So I can expand that. So let me use some color here. So S, and I have really having two options here. One option with 2, one option with 3, right? And at 2, I have really having two options here, right? So I can either go to by one coast and I reach the goal, or I can do 5 coast and I reach this node, which is 1, 2, 3, let's say. This is 4, let's say, right? And similarly 3, then I have reached to 2, reached to 1 here. I can have only one option here. So I option here 6. And this will also reach me to 4. So if you expand like this, you will get a like tree, and such tree, if you really enumerate, like if you find all possible paths, one of the path will be what do you call the optimal path, right? For example, here I can either go to 2 and 1, 3, or 3 and 6, 9, right? So then I will definitely not choose. So what I will choose at every stage is the list one. Now the problem here is um, choosing the list one sometime may not be optimal, right? So it's not always true that if you choose the list at that particular position, you are going to get the best possible solution. That's not true. And why that's not true is because, let's take this example where you have, this is the start state and my goal state is somewhere. So let's say 1 here, 100 here, and this is 1, and then this is my goal state G, this is 2. Here my cost is just 1, but here my cost is 200. So in such scenario, this greedy method, which is like choosing best at current position, right? So if you are current position, whatever is best, you choose that, right? So if, for example, 1 and 100, I will choose 1, and then 200. So 200 plus 1 is my cost, right? But if I would have chosen this particular path, right? I have chosen this particular path, then my cost would have been 100. So, sorry, 101, 100 plus 1, which is definitely better, right? So this greedy method may not be always giving you the optimal solution. And therefore, when we talked about uniformed, or sorry, informed search, what is informed is usually the how far it is from the goal, right? So at every state, you know how far the thing you're talking is from the goal. So in A star, that's what happens is you have a start state and you have this nodes goal there. At every step, you also know how far it is from goal, right? You know 200 a priori, you know 1 a priori, you know this S is like some distance, S and G are and some apart from this. So these values are known, and then your decision is based on these values, right? So you actually use this value to determine, and that's what is the A star search. Okay, so this is just a brief discussion. I think this is something which you know better uh, already. So let's move to our presentation. Okay, so I'll go to presentation again. Okay, but this is a search technique, and the search is used for problem solving. But problem solving and planning, these two things are slightly different, right? Planning is not just problem solving, but much beyond that. And we'll see what is this. And in next couple of lectures, we will be clear what is the really difference between the search or problem solving versus planning, right? So planning is in artificial intelligence is about the decision making tasks performed by the agent to achieve a specific goal, right? So let's look into the example of planning as problem solving. Okay, so what I mean is we have this problem, let's say, where let's say a robot is moving in certain rooms, right? So these are different rooms. A is one room, B is another room, and so on. So there is a K room where K is, let's say, K stands for kitchen, and you are in different rooms, and you are supposed to, you are asking robot go to kitchen and yeah, let's say go to kitchen. So kitchen is the goal, K is kitchen, and all other rooms we should able to operate the we should have a set of instructions for the robot so that it can reach to K. It is a very simple problem. So you can have different start location. So let's assume that my start location or start state is S. Sorry, C. So my start state is C. Now my goal is to reach. How will I reach? I'll have to apply certain operations, like you can easily see here. If I move to north, sorry, so there are operations here. Move north. If I move in this direction, right? So I hope you can see my cursor, and move east, right? So this direction. Move west is this direction, and move south is this direction. So this is four directions agent can move. So easily you can see I can move to north, right? So I can move, sorry, I can move to east. I cannot move to north here, right? Because there is an obstacle here. So this black part is an obstacle. So I cannot really hit to obstacle. So I cannot really move to north, but I can definitely move to east, right? I can also move to west. There is no problem in that. But I choose to move to east, for example. So then I have only one option here that I move to where? North. I move to north. I move to north again, I move to north again, and I move to west. And that's it. Right? So I reach the goal. Very simple, but this rules or the set of actions, right? The sequence of actions is really dependent on where my start state is. If my start state would have been different, I might have different set of instructions. But that's really something not always feasible in a very large scale setup. And especially if you do not know, for example, let's consider the scenario where you do not know where the start state is. Right? That's possible. Uh, If your start state is unknown, then how will you approach this problem? When I say start state is unknown, my agent is either at A, B, or C or D, let's say. But I really don't know whether it is for sure that whether it is at A, B, or C or D. So in such scenario, if I try to model this problem as a like simple instructions and search type, then what happens? Let's look into that. So by initial state, right? So which is A, B, C, D. My initial state is A, B, C, D. What does it mean? My agent is any of these locations, right? So any of these states, my agent is in. So I'm using locations and state interchangeably here. For this particular example, it is making sense, but they are not really the same. So A, B, C, D we are in, and if I move to north, what happens? Right? So this is interesting. If I move to north, what happens? I can move to north from A, and then I can reach to E. Right? If I am at A, I can move to north and reach to E. B, I cannot really move to north. And if you say move to north, because I'm going to hit the obstacle. So B, you cannot really move to north. C, you cannot really move to north, but D, you can move to north and reach F. Right? So therefore, this is E, B, C, F. P and C are unchanged. Similarly, if I'm at these positions, if I am asked to move east, right? So A will be moved to B, this will be moved to C will be moved to D, but D there is no option to moving, so the next state is BCD, right? So this set of states is nothing but these are the possible locations where my agent can be, right? One of these locations my agent can be. And then I can keep expanding this. In the next slide, I can see that I can keep expanding. So I can, let's say, EBCF. What I can do is again move north or again move east, whatever, all operations I can. I'm not writing it here, but you can actually make a very large tree here, where from E I can move to G, F I can move to H, but BC will remain same. Because BC I cannot really move to north. CD, if I move to east, B will be C. C becomes, this will become D. So we'll have only options CD. If I keep moving like east again, so I will remain with only one D, right? So if I east and then one more time east, I will remain D, and then I can north, then there is only one state I can move north three times, and then west I'm done. So you can see that this graph can actually give you some solution, find it. But what is happening, if you notice, is this graph is not going to be very easy, like very small graph, right? So for very small trees, this is going to be very large tree, because if you consider all possible things, there will be multiple subsets, right? So this all what you say states, these are the subsets of the states. So these all are the subsets of the states, and you are really dealing with the subsets of the states in this graph. So that's a problem. Uh, if you have, let's say, thousand states, having thousand states is very very trivial in a real world scenario. You typically have many more than that. But how many nodes such tree can will have? Anyone can answer? If you are talking about, let's say, thousand states, and you are trying to model all possible states, that will be 2 to the power 1000, right? And that's what is the problem. And if 2 to the power 1000 is like 1 10 to the power 300 or so, very large number, and that becomes typically very unfeasible, incredibly inefficient way to work in. Type of transitions and searching in such a space is incredibly inefficient technique, right? We should avoid possibly. So therefore, instead of planning as a problem-solving approach, people move to planning as logic. So when I say planning as logic, can we formulate the planning problem using logical description of relevant sets of states? So what does it mean? Let's look into this same example. So all these states like A, B, C, D, they can be represented as one set, right? So they can be maybe one logical, they can be clubbed in a one logical statement, like they are in the row one or something like that. So that's what we are going to do here in the situation calculus. So this planning as logic that leads to situation calculus. Like first, we need to understand what situation calculus is, and today's lecture is primarily towards that, where we are trying to understand some part of situation logic, and then we will see how situation logic is used for planning, and beyond that in the next lecture. And so situation calculus, have done this before in AI1 or somewhere? No. Okay. Okay. So this is, we'll see situation calculus is. So a situation calculus is like dealing things with logics mostly. So a situation is a logical term. Right? A situation is a logical term, and initial term is called the initial situation. Right? So you have so initial situation is like all things are set in the environment, and robot is at certain, or agent is at certain position. Everything is every position, everything you know, right? So initial state is that. So that's initial situation. And if you do something, so any perform action you perform, any term generated by applying an action to a situation, that will give you, so let's say S0 is your initial situation. If you apply some operation, so A is action, right? So if you apply action in this particular situation, then the situation will change and you will, let's say, get a new situation S1. So this looks very abstract, but let's look into the example, a very, very simple example I have here, which will give clear idea what we are talking. So this is a scenario here. We have 4x4 grid. Like this is the Tom and Jerry, right? So Tom and Jerry, and then there is a cheese. So the Tom is cat, right? So Tom is cat, Jerry is mouse, and this is 1 1 1 2 1 3. Sorry, 1 1 2 1 2 3 1 4 1. Right? And similarly, this will be 1 4 actually. Let's correct it here itself. This should be 1 4. And that's 4 4. Right? So this is initial situation. So these are the two agents. Jerry is one agent, Tom is another agent, and this cheese is not an agent, but these two are agents, and this cheese is kind of a goal. So the goal, the task is here to we need to send this Jerry to, let's say, eat this cheese, but he should escape, or it should escape from the Tom, right? If Tom is stable, Tom is not moving, let's say, Tom is at this particular position, but Jerry can really move, and but it should not collide with Tom, otherwise Tom will eat Jerry. So this is sitting, right? So this is what type of environment is this? Anyone we discussed yesterday? Uh, is it a single agent, multi-agent, dynamic? Yeah, it is static because things are not really changing, right? It's it is not collaborative. It is multi-agent because we have two agents. This is a stable agent, but it is still, it can eat Tom. Tom can eat Jerry. So we have this agent, and Jerry should survive. So therefore, it is competitive. It's not collaborative. And this is the scenario, right? So this scenario is like initial situation. Now, if Jerry moves from room 1-1 to room 1-2, I think this is be 2-1. Okay, this is a typo here. This will be 2-1, let's call it. Right. So 2-1, if it moves, the world is changed, right? And we have a new situation. How do you express that situation? That is all about the situation calculus, right? So so this is what is happening here is in the situation calculus, as I said, this uh, this is an action, right? So this thing which is in red, that's the action. So action is go room 1-1 to 1-2, right? Okay, so let's keep it 1-1 to 1-2, and in the situation S0, and whatever, if you do this, you will get a new situation which will be S1. So this is a new situation now. You can see this. So this is a new situation where S1. So this situation calculus is like describing in this type of logical statements where there is, as I said in this, let's look into the definition again. This situation calculus has only two terms. One is the initial situation, which is S naught, and other one is you apply something on S naught, some action. So here, if you can see, we are applying this go statement, right? Go from this room to that room, and that's the action, and this is the initial situation. All right. So there are yeah, maybe that's also true. It is not multi-agent. Tom can be treated as threat only. Yeah, if Tom is not really acting, maybe yeah. So it's kind of obstacle or something which you can agree with that. Let's call it single agent that way. Okay, so terminology with all these terms, the definitions of all these environments, they very subjective, and how you model the problem and how you define that depends on that. So that's not really take it the definitions as pinch of salt. So you can always modify this, right? So that's okay. But let's understand the terminologies a little bit more. So, affluent, right? So, this is the terminology is related to situation calculus. So, fluent is a function or a predicate that vary from one situation to the next. So it's a function or a predicate, and by convention, the situation is always the last argument of fluent. Let's look into the example. So this type of things, how do you represent such thing in situation calculation? No, no. So we can, if you model like that, like Ranjan has a question here. So Tom has two goals. As of now, we are just not having two goals. Tom is not eating butter. Or that cheese. Tom is like stationary there. So yeah, if you can, if you model like that, then definitely this will be multi-agent. Okay, so Jerry holds some cheese in the situation S. Right? And the other example is the age of Tom in situation S. How do you represent that? So this is how we represent holding each C. C is actually you can read this like C is a cheese, and at situation in the situation S, this is holding. This is Jerry is holding, right? Because actually here we are assuming that only Jerry is moving and it can hold cheese at some particular time. So here we are not writing Jerry at all, right? So here we are just saying that situation is yes, C is a cheese and it is holded. And when it is holded, we are assuming that is holded by Jerry, none other. The age of Tom in the situation S, right? Age of Tom, age situation F. This is how we represent age of Tom at situation S. And every situation, the age will be varying, right? So this is like how much time it has passed. So this is age of Tom at situation S. These things are called fluents. So fluents are nothing but some arguments where you have a situation and something you describe, right? So in that situation, this is not something which is universal. What I mean to say, this is not universally true. This is only true at that particular situation. This will change as the situation changes, right? So fluent is can be understood that way. But the other one, which is atemporal predicates or functions, they are slightly different concept, or in they are kind of a universally true. Atemporal means whether the time passes, they are like independent of the situation. They are true, right? And atemporal predicate or function is a predicate or function that do not vary from one situation to the next. So they are independent of the situation. So, for example, Jerry is a mouse, right? So it is a mouse, and that's a known concept, and that's not going to change with this change of situation. Right? So in this atemporal predicates, you will never find S arguments. So S you will not find because they are inversely true for the entire setup. For example, another example, position A is adjacent to B, that is universally true. Right? So if the A is adjacent to B, for example, 1, 1 is adjacent to 1, 2, that's universally true, and with change of situation, that's not going to change. So these are temporal predicates. Okay, now let's look into some of these actions. This is again, this will be more clear when we talk, see the examples, but just let's see what the definition says. So the definition is like axioms. An axiom is described with two axioms. One is possibility axioms, when it is possible to execute the axiom. So if given some condition, whether that is possible to execute that action, right? We'll see the example. Let's do not worry about what it's saying. Effect axiom, what happens when the action is executed? So when some action is executed, change the result that results from taking action A in situation S. Let's again move to our Jamboard and see the example so that it will be more clear. So let me share the screen. Just a minute. So the things, these axioms we are trying to see in this same Tom and Jerry example. Uh, so because our agent is here, agent is Jerry, right? In this example, and taking example of possibility axioms. Right? Possibility axioms. How things are represented, right? So let's take one example number one, where a Jerry can go between between adjacent locations. So this is a statement, and how do we represent that? Jerry can go between adjacent location, adjacent location. Right? Jerry can go between adjacent locations. So in this, how do you model? First of all, you have to assume where Jerry is, right? So we can write at Jerry X S. What does it says? Jerry is at position X in the situation S, right? Jerry is at position X in the situation X. And you can clearly see this is nothing but a fluent, right? It's a fluent. Other one is you need to know what is adjacent, right? So you need to know what do you mean by having adjacent. So you can write it that this is one thing, but the other thing which is also I know that adjacent. Right? So ADG is XY. That's it. X and Y are adjacent to each other. And so what are these two sentences statements saying? The statements, one is saying, so this part is saying that Jerry, let me write it, Jerry is at X in situation S. All right. And this part is saying that X is adjacent to Y. Right? Or X and Y are adjacent. So if these two things are there, what is the possibility? Yeah. If these two things are given, so Jerry can go between adjacent location, right? So the possibility is go, right? X, Y, and situation S. This is the possibility. So this is called possibility axiom. So possibility axioms, this whole thing, this is called possibility axiom, where and these two statements are true. That means that implies the possibility is you can actually go from X to Y in situation S, right? Because that is what we is given. Let's take another example. Any question here? Okay, let's take another example. Uh, This is also interesting where it is saying that Jerry can grave some some cheese, cheese in the current location, in the current location, right? What is it saying? That Jerry can grave some cheese in the current location. So we need to see what is cheese. So we will first define what the cheese is. Cheese is as a variable. Cheese. C is a cheese, right? And let's say this is for and. So this is and. Let's say Jerry is at location. Jerry is location S. X at situation S. All right, and then what we can say is Jerry can grab cheese in the current location, right? So where is cheese? At which location? At which location cheese is? Anyone? Jerry is at X. Cheese must also be in the X. Then only this is we are trying to describe. So cheese must also be at X. So cheese C must also be in the X and in situation S. All right. So this is what we're trying to say, that the entire of statement we are trying to write. Jerry can grab this part we have not written, but some cheese in the current location. So if Jerry is at location X and cheese is at location X, right? Jerry is at location X, cheese is at location X. If that is happening, then there is a possibility of grabbing C at situation yes. Okay, so this is example 2 where we have seen this possibility axiom. The third example will be making it more clear perhaps. So third example is let's say Jerry can release Jerry can release some some cheese in the current that it is that it is holding. So we can write it like holding CS, right? So whenever we say holding, it really means the assumption is Jerry is holding, right? So that's the assumption. But holding cheese CS, that's what is given, right? Jerry can release some cheese that it is holding. So holding CS, and this will lead to possibility like pause, release C. Yes. Okay, so this is how you write possibility axioms. The other one, which is called effect axioms. So we'll give some more problem today, so which will make it more clear. But let's also look some examples of effect axioms. So effect axioms, we said you have some possibility given, right? And then you describe it. This is like the other way, right? So what happens when the action is executed? So let's look into one example, like example one. Jerry goes between between adjacent location, right? So if what is the effect of that? So Jerry goes between adjacent location. So we can write it possibility go x y s. This means that what will be the like if Jerry is at position x, if I apply this go x y, Jerry will reach at y, right? So Jerry, this is nothing but at Jerry is at y location, and this is the result of slightly complicated, but once you do practice, it's not that hard. X y, yes. Right? So Jerry can goes between adjacent location. So what is the effect of this particular operation or possibility of going x to y in situation x? If Jerry was at a position x, it will reach to position y because of this operation, right? And this is that. Okay, so the material which I will share will have some more examples, but I also have some more questions for you to try, so that will give some more idea. Let me share that. All right. So, yeah. Just a minute. Okay, so I can see some answers. That's good. But okay, which among the following is not a temporal predicate or function, assuming as is the situation? Uh, so whenever atemporal means they will not going to change with the time, right? So if A is north of B, that is not going to change with time. If mouse is at 11 position 11 uh, in situation S, that can change with the time. Tom is cat, that's a universal truth, that's not going to change with time. So wherever your the S is there, that's temporal, right? These are all temporal. Let's see some questions. So the what is the correct answer here? Uh, cat is Tom, that's atemporal, right? Predicate. Sorry, Tom is a cat, that is atemporal. A is B, north to B, that is also atemporal. But mouse, it should be like wherever S is there, that should not be the correct answer, right? So because that is with situation it will change. So atemporal predicates are something which are independent of situation. If a location A is not to be, that's independent of situation. But if something is dependent on situation, that's not going to be atemporal. Okay. So moving to next question. So others, please respond. Maybe can take a couple of minutes break here. So just 35 response. Maybe others are okay. Let's look into next. So this is consider a chess game. Okay. Suppose pawn is an agent, right? Pawn is that the smallest element in the chess, and it's at position X. Now, write possibility axioms for the following statement. The statement is pawn can to go to either north, northeast, or northwest. How will you write? Try writing. So this will give you some idea what is. So if you remember, we have done this similar question, like Jerry can go between adjacent location, right? So first of all, where is Jerry, right? Something someone has tried. Of course, the go to north or go to northeast and go to northwest. Uh, Completely correct, right? Yeah. So this is at pawn is at X. There was some response I can see. Then pawn can go to, yeah, some changes will require, but good try. Pawn northeast, no. Try to refine the answer. Maybe first thing is you need to assume that where the pawn is, right? So that should be there, and then you should have and multiple ors, right? So you need this or that or that. Yes, so this is something is good, but this is there are multiple or. It should be pawn is at X and then ors, right? So this will be combination of and or. Okay, maybe I can answer this. Okay, giving some time, maybe you can think. Yes. So pawn at X. So this is something which is sorry. Yeah, so this is something pawn is at X, then pawn can move to north, but this situation is missing here. Some changes, yeah. All right, so next question. Uh, Write fluent for the following situation. Okay, a robot R is not holding object O in situation S, but it is holding the situation resulting from S by picking O up. So there are two statements, two parts, right? Two clauses. One is it is not holding object O in situation S. How do you write it? First part, a robot R is not holding. So not holding, I am not saying the statement not, but you can write something like not. No holding, that part is fine, but the next part also, this is part one. Someone has given answer that not holding object OS. This is part one. But then there is a part two of that. It is holding the situation in the situation resulting from S by picking up O. How will you write? So this is correct, the part one. But then you have yes. So someone is trying not holding pick arrow situation. Yeah, so you guys are trying. Maybe the right answer will definitely discuss these two questions next time. But you think about this. How do you try to write? Because maybe you should look back at the lecture and try to see how to write fluent. Fluents are not possibilities. Uh, Fluent are just some statements. Okay, so what we can do is these two problems we will start from the when we next time, uh, and we'll write, and then we can. So the next week we will continue from this situation calculus and then state space search, partial order planning, graph planning. So uh, that's the thing we should do. Uh, so let's. So this is one reading material which is read about this situation calculus. Very nice article, and from where this is where I took the examples of this Tom Jerry. Uh, Very clear most of the part. So definitely look into this before we meet next time. Uh, and yeah, so these are the some references. So let's meet next week, and we will start from whatever we discussed. Have a look into this PDF before we meet next time. So this week you should definitely have a this whatever reading materials I have given yesterday, and uh, please look into that, and let's meet next week. Okay. All right. So thanks for joining, and let's meet next week. Thank you.